The CPU, or Central Processing Unit, is often called the brain of your computer. It's responsible for executing every instruction that makes your programs run. The CPU contains several key components that work together. Let's examine the main parts: the Arithmetic Logic Unit, the Control Unit, and the registers. The Arithmetic Logic Unit, or ALU, is responsible for performing all mathematical calculations and logical operations. It can add, subtract, multiply, divide, and perform comparisons between data values. The Control Unit manages the execution of instructions. It coordinates all CPU operations, tells other components what to do, and ensures instructions are executed in the correct sequence. Registers are small, extremely fast storage locations inside the CPU. They temporarily hold data and instructions that the processor needs immediate access to during execution. The CPU operates using a fundamental process called the fetch, decode, execute cycle. This cycle repeats continuously, processing one instruction after another. During the fetch stage, the CPU retrieves an instruction from memory. The memory address is specified by the program counter, which keeps track of the next instruction to execute. In the decode stage, the control unit interprets the instruction to determine what operation needs to be performed and which components will be involved. Finally, during the execute stage, the ALU performs the actual operation. This might involve calculations, data movement, or logical comparisons, depending on the instruction. To better understand how the CPU communicates with memory, let's look at the interaction between these components. The CPU uses buses to transfer data, addresses, and control signals. Modern CPUs use advanced techniques to improve performance. Pipelining allows multiple instructions to be processed simultaneously in different stages of the execution cycle. The ALU itself is a complex component made up of logic gates that can perform different operations. Here we can see how ALUs are constructed using basic logic components. Branch prediction is another important technique where the CPU attempts to guess which path of code will be executed next. This reduces delays and keeps the pipeline flowing efficiently. This continuous cycle of fetching, decoding, and executing instructions, enhanced by modern techniques like pipelining and branch prediction, allows the CPU to process complex tasks efficiently and power all the applications you use every day. A CPU's clock speed, measured in hertz, determines how many instructions it can execute per second. The clock acts like a metronome, synchronizing all CPU operations. Modern CPUs have multiple cores, independent processing units within a single chip. Each core can execute instructions simultaneously, dramatically improving performance for multitasking. Caches are small, extremely fast memory areas built into the CPU. They store frequently accessed data and instructions, reducing the need to access slower main memory and significantly speeding up operations. Hyper-threading technology allows a single physical CPU core to appear as two virtual cores to the operating system. This enables better utilization of the core's resources by running two threads simultaneously. Modern CPUs integrate many specialized components beyond traditional cores. They include graphics processing units for visual tasks, AI accelerators for machine learning, and advanced memory controllers, all on a single chip.